The objective of this video is to determine the impedance and bar currents of a cage winding rotor. In a previous video, we've learned how to calculate the slot voltage, or the bar voltage, of a cage rotor given the total air gap field and given the rotor speed and the speed of the air gap field. So we know how to calculate the voltage that is acting upon a rotor bar. The question now is that when we have the rotor configured as a cage rotor, what is the current that flows in the bar? So given the bar voltage, what is the rotor bar current? And so you can see here I've crudely sketched on the left a cage rotor where the slots are spaced by alpha c. And in our previous video, we learned how to draw the star of slots for this, given information about what harmonic we're looking at, the rotor speed, all this information. We can take that and we can draw the star of slots for our voltage phasors. And you can imagine that we can then take a step further and sketch the electric equivalent circuit of the rotor. And so I've done that here on the right. You can see that this right here is a rotor bar, so that corresponds to one of these bars in our squirrel cage rotor. We've got our rotor end ring at the top and bottom of the rotor, and that corresponds to these loops out here. Our rotor end ring has resistance associated with each piece of the ring. So between two bars, we're going to have some resistance, that's denoted here. And we're also going to have some leakage inductance, which is flux that links the end ring of the rotor, but doesn't cross the air gap and link the stator winding. Similarly, on our rotor bar, each bar is going to have some finite amount of resistance, as well as a certain amount of leakage inductance, which again is flux that links that rotor bar but does not cross the air gap and link the stator winding. So every single bar is drawn here, along with its leakage inductance, its resistance, and the end connection resistance and leakage inductance. And so the question at hand here is, all right, if we know each of these voltage phasors that are acting upon the rotor bar, what is the actual rotor bar current? And so we have a couple cases that we can consider for how to answer this question in terms of what harmonics we're looking at. And the first case is the trivial case, so let's talk about that first. That is when we actually end up with no rotor current. And so it turns out that if you, as you can probably imagine, if you pick a harmonic V where all of your phasors and your star of slots appear at the same location, you won't get any rotor current. Because you can imagine that if this voltage phasor is the same as this voltage phasor, is the same as this voltage phasor and this voltage phasor, if they all have the same magnitude and the same angle, it is impossible for any current to flow in that rotor. So again, our star of slots looks like this. All phasors are at the same location. And we can also understand this by drawing a fields diagram. So we can say that at this harmonic, there is no field that links the rotor cage. And this is my crude attempt at drawing how this would look. So in this case, we're plotting what B delta of alpha looks like. So here's around our rotor periphery or air gap periphery. And you can see that at this harmonic, we have a field that has exactly one electric cycle between rotor bars. So there's no total flux linkage that links any mesh of the circuit. So if you were to integrate the flux going through this cage here, you'd see that that corresponds to this right here, and there's 0 Webers of flux. And so therefore you cannot possibly get any d phi dt. You can't possibly get any net voltage in there. Now that stands in stark contrast to a full pitch coil, in which case your B delta would look like this purple curve that I'm drawing here, where it links exactly one pole. So in that case, you'd have a full pitch coil that you have 100% flux linkage. And so we can understand this from our coil pitch factor perspective as well. So this coil, this arrangement that I've drawn up here, corresponds to when our coil pitch factor is 0, if we were drawing these for coils instead of for rotor bars. So that was the first case for how to solve this circuit. It's a trivial case because there's actually no current. we can determine harmonics for which this condition is met, and if those harmonics are present in our air gap field, they will not induce any current in our rotor. The second case is the more practical case that we have to concern ourselves with for how the machine operates. And this is the case where flux actually does link our rotor. So I guess that I'm starting by stating a fairly obvious thing, which is that we're going to have a star of slots where the slot phasors are spaced by VP alpha C. We've already acknowledged that up here. So we've already recognized from a previous video that when you have a mechanical spacing between two bars, you're going to end up getting a spacing in your star of slots of VP alpha C. So nothing new there. That's kind of a trivial thing to say, but it's interesting because it means that your total your cumulative rotor is going to consist of all these voltage sources here that are evenly spaced. They're the same magnitude and then evenly spaced phasor directions, and that's going to have important implications as we move forward in trying to analyze this circuit. And I'm now going to sketch just a part of it to try to zoom in on some critical features. So I've drawn this circuit here, which you can see is just me having extracted this part of the circuit up on top. And this is going to make things a little easier to have it look a little bit more like a conventional planar circuit to us. And the first thing I want to draw your attention to is that we are using the generator sign convention. So here you can see our bar voltage source that we've determined in our previous video, and the direction of the bar current is leaving the voltage source. In other units in the class, we're using the motor sign convention, where the current enters the positive terminal. Here you can see that the current is leaving our positive terminal. And so this circuit, or rather this complete circuit up here, is something that can be solved using mesh analysis techniques. You can write this out for the circuit in general. It will give you a lot of equations that you can solve simultaneously to get a solution. But we are going to make some observations about this circuit that are going to allow us to solve it much more simply. And we're going to do this in steady state. So that is, we're going to define impedances and solve a set of complex equations. And to make our notation simpler, I'm going to right away define a complex impedance for the rotor bar. So that would be this region. And a complex impedance for the end connection, the end ring. And so there's nothing surprising here. Our bar impedance consists of the rotor resistance plus j omega times our bar leakage inductance. And the omega is our rotor frequency, which is equal to our slip times our stator synchronous frequency. This was, again, a result from our previous video. And then we do a similar thing for the stator end ring. It's the end ring resistance plus j omega times our leakage inductance. And we're going to make the following observations, which will then simplify our analysis. The first observation is that our phasor for bar number 2 is equal to our phasor for bar number 1, but rotated by VP alpha C radians. And that we know from drawing our star of slots up here. So here's our bar 1 phasor. Our bar 2 phasor has been rotated in the clockwise direction by VP alpha C. And since we can say that, we can also observe that we're going to see the same rotation in our currents. So that is, IR2 is going to be rotated from IR1 by that same angle, and IE2 is going to be rotated from IE1 by that same angle. Next, we're going to solve an equation for our end ring currents in terms of our rotor bar current. So we can write this equation just using KCL, that the current from bar 1 plus the current from end ring 1 must equal the current in end ring 2. So this current plus this current must equal the current that's headed this way. And then from this, we can use our relation up here that IE1 is going to be equal to IE2 times e to the j VP alpha c. And we now know our current in end ring 2 as a function of our bar current in bar 1. So that's going to come in handy in a little bit. But next we're going to write an expression for our voltages around this loop. And so we get this expression here, which we obtain just by summing up that UR1 must be equal to this voltage drop, plus this voltage drop, plus this voltage drop, plus this voltage source, and this voltage drop, which is what this set of equations is describing. Now we can start rearranging this to take advantage of these relations that we have up here. And we get this expression here where you see that UR2 is coming, we're plugging this in for UR2 and simplifying. Likewise over here, we're able to pull IR1 out by taking IR2 and substituting this expression in. And then right here, IE2, we're recognizing that we already have that in terms of IR1. So now we're prepared to rewrite this expression where we're going to pull IR1 out of the right-hand side and group like terms, and we get the following. And now we've arrived at a rather interesting point. We have this equation which tells us how to get our rotor bar current from our rotor bar voltage, which is exactly what we wanted. We can call this term in the middle here our equivalent phase impedance. And while this does what we want it to do, it's not in the most convenient form. We don't really like to see all these e to the j VP alpha c terms in here. And so we can work on those terms and convert that into a more convenient expression. And so by working on this expression, the denominator of our impedance, we're able to get it into a sine equation, which is a much more convenient form. And if you'll notice, this equation right here, sine squared VP alpha c by 2, that is simply the square of our pitch factor that we had up here, which tells you something interesting right away. Because remember, we had talked about this case up here as corresponding to when we get no current in our rotor. And so we can see right here that if sine of VP alpha c by 2 equals 0, this denominator is 0 and our impedance is infinite. So this impedance expression actually predicts that for certain harmonics you will not get current in the rotor. And if we work on that expression, we can see that this is also the same thing as saying that VP alpha c leads to a 0 result, 0 current for 2 pi, 4 pi, and so on. And again, that matches our observation up here for when no current flows. So what we'll do now is we're going to go back to our definitions for ZB and ZE, and we're going to collect out the resistance terms and the inductance terms. So right now we've got a ZBV here and a ZRV here, so we're just going to plug back in these expressions and collect out our resistance and inductance terms so we can talk about the resistance and inductance separately. And you'll see that when doing this, I've used sine squared of VP pi by QR. And this is the same term. I'm just simply making the observation that alpha c is equal to 2 pi over QR. And so then we finally get this nice result in the blue box here, which is we can talk about our equivalent rotor circuit resistance as this RRV and our equivalent rotor leakage inductance, which is this LR sigma V. And the V, again, is keeping track of harmonics. It appears inside this sine term. And our total rotor impedance, the ZRV, we oftentimes are going to talk about it in terms of its magnitude, so ZRV hat, and angle, which we're calling zeta RV. So remember this is going to come up frequently in our induction motor unit, the magnitude of our rotor impedance and the angle of our rotor impedance, as well as the resistive portion of our rotor impedance and the leakage inductance portion of our rotor impedance. All of these are going to come up time and time again as we talk about asynchronous machines. These quantities in this box, we're not going to spend much time figuring out how to calculate these individual resistances and inductances, but if you're interested in this, I will point you to your book. The resistances, you can take a look at chapter 5. Resistances are fairly straightforward to calculate. DC resistance, and then you can consider AC resistance at different frequencies. So the fact of the matter is that we write this expression as if it's a DC quantity, but in all actuality, resistance changes with frequency, especially in a cage rotor where you have significantly sized rotor bars. And when you are at a locked rotor condition, your frequency conditions in the rotor are high because S is equal to 1. But when you are at rated load or at no load, S is typically very small, and then your frequency is low. So chapter 5 will tell you how to calculate your resistances, and these leakage inductances, see section 4.3 of your textbook. Okay, so with this observation, we can start to notice that our electric circuit becomes very simple. And I'm going to draw it in a few different ways here. So first, I'm again drawing our squirrel cage rotor, but now you'll notice that I have pulled the end ring impedance into the rotor bars because evidently you can do that. That's what our equation tells us. So I'm showing this RRV right here as the equivalent resistance that's in series with our voltage source, and an LR sigma V that's in series. And so that's our first case. This is a much simpler circuit to solve because there's no impedance out here where the neutral connections are. Second, I'm going to kind of blow this circuit up and try to draw it as a planar diagram. I have taken this circuit and I've just resketched it over here. So if we start down here with this connection here, that corresponds to this neutral point right here. And then you can see that each of my voltage sources is appearing going outwards. And then we've got our inductance and resistance. And finally, this end ring up here is drawn as yet another neutral point over here. So because each of these voltage sources has the same magnitude and their phase angles are equally distributed from 0 to 360 degrees, we can conclude that the voltage between the two neutral points, so between this point and this point, we can conclude that this is 0 volts. And to be honest, I'm not really saying anything revolutionary here. Actually, all of the information I'm giving you was already predicted up here when we made this observation that UR1 is equal to this impedance times IR1. But I think it's instructive to see this in equivalent circuit form, so we'll keep going with this. Next, I'm going to take our observation that there is 0 voltage between these two neutral points and use that to draw a circuit that just consists of this. And we can observe that this is possible because there's zero voltage here, so you could provide a current path between these terminals. You could short circuit these terminals, and it wouldn't matter. It'd be the same thing, right? 0 volts or a short circuit is the same thing. And so that's effectively what we've done. And we also know that this is true because, well, these two elements combined make ZRV, and that matches our observation right here for how the voltage and current relate to each other. This equation is this circuit. From this, we're kind of making a subtle observation here, which is that each of the rotor bars of our squirrel cage winding ends up being a single phase. And that's a little bit counterintuitive because a single rotor bar is like half a coil, right? It's one side of a coil. And yet you can see that when we short circuit the top and bottom of our bars, we end up having each bar behaving as a single phase. Finally, the last thing I want to point out here is that we've actually accomplished quite a bit today. We know that we can start with an air gap flux density. We can start with our magnetic loading of our machine and knowledge about how fast it's rotating and how fast our rotor is rotating. And we can use that to calculate what our voltage is going to be in any given bar. And then we can use that and now figure out what the current in any given bar of our rotor is going to be. Okay, so that concludes this video. I'll summarize quickly what we've learned. Again, this video is tackling the question of rotor impedance and bar currents, and we talked about how we can take our squirrel cage winding and we can draw the star of slots for it. We summarize that, and we can then draw an elaborate equivalent electric circuit for it in terms of leakage inductances and resistances. We talked about conditions for when you can get current in your squirrel cage rotor and when you cannot, based on the bar spacing, or in other words, based on the number of rotor bars and the harmonic of the air gap field. We have also talked about how to solve this equivalent circuit in a practical way, and done that to, in fact, arrive at effective rotor impedance resistance and rotor impedance leakage inductance that depends on this funny term in the denominator, which shows that we're going to get a different value of impedance for any given harmonic that we're considering, and that this impedance in fact tells us when we can get current in our rotor and when we can't, because for harmonics that are incapable of inducing current in our rotor, our impedance goes to infinity. And finally, we concluded by showing that we can consider each bar of our rotor as being a single phase of a multiphase winding.